Sorry about that, guys. I'm not even gonna lie to you. That, whenever it cut off and I heard my own voice, I got scared. Like, that was... I got super scared. Because imagine you're just trying to say something, all of a sudden you just start hearing something from in front of you. I got super scared. But anyways, if you can explain how energy and entropy are changing in a variety of scenarios, it's complicated. Energy and entropy, it's just what it is, right? I can define energy. Are you serious? All right, this one's a bit more simpler than I thought. All right, so energy is actually just going to be the ability to do something, work, right? So let's say that this pencil, you can't really tell here. This pencil is up off the ground, right? It has a good amount of energy. Now it has less energy because I dropped it. That's energy. I can explain how energy is transferred between a system and its surroundings. We already did that, by the way. So I can identify the parts of a calorimetry experiment. Easy enough. You know, you got whatever you're burning. You got your liquid. Oh, well, the equation, if you just really need that, it's going to be... Here, I'll pull it up. The parts of a calorimetry experiment, well, all you're really going to need is the calorimetry equation. Q equals mc delta T. What does that mean? Q is going to be your heat gained or lost in joules. Your M is going to be the mass of the substance that you're measuring. So if you're measuring like a cup of water, you're going to be measuring that. That's your mass. C, the specified heat capacity. Sometimes it'll ask you to solve for this. The specified heat capacity is basically just how much energy it can take in before it heats up. So, for example, water with a specified heat capacity of 4.14, that just means that it can heat up. It'll take, I think, 4.14 joules of energy to heat up by 1 degree Celsius, right? Now, delta T is going to be your change in temperature. So, it's going to be the final temperature minus the initial. That's what's going to get you your delta T. All right, so we just identify the parts of calorimetry. Identify types of data that we can attain. Well, types of data that we can attain is obviously the heat gained or lost in joules. So like I heat a cup of water up to 20 degrees Celsius from 0. You can obviously calculate that by saying, let's say the mass of the cup was like 200. You could say Q equals 200 times 4.14 times, I think like 20 minus 0. Which is that's how you calculate the heat gain from that. Now, we already did that. I can identify the types of data that we can attain. Well, you can obtain, the heat gained or lost. You can also calculate for the mass, and you can also calculate for the specified heat capacity of whatever you're measuring, which is a bit more complicated, but you can do it. I can collect accurate data for a calorimetry experiment. Well, you can probably obviously do that. I can use calorimetry data to describe how energy is flowing between the system and surroundings. Well, essentially, you can say, let's say that example that I just said at 20, let's just say, this, right? I heat this up to 40 degrees Celsius. That'll make it easier. 40 degrees Celsius. So we're going to heat that up, and now it's heated up, right? Now, let's just say the pencil was the one who was heating it up. We can say that energy was moving from the pencil into the water bottle to heat it up, or into the water itself. So, yeah, you can obviously do that. I can design a calorimetry... Okay, y'all can probably already design a calorimetry experiment, because, we literally did that in class. Now, learning target 3, classify process as exothermic or endothermic, and represent energy changes that occur in chemical reactions using thermochemical equations or graphical analysis. I can define endothermic and exothermic. Easy, all right? Exothermic. Always remember, exothermic. It's going to be exuding heat, right? Which means that it's... Hold on. All right, easy enough. Let me get rid of this for you real quick. Sorry about that. Exothermic, essentially, you can imagine it like this. Exothermic. Let me write that down. Exothermic. Exit. That means heat. This is heat. This is our object. Heat is leaving the object. So heat is leaving the object. So it's exiting heat. There's heat coming out of it. Endothermic. Y'all can't see that, sorry. Endothermic. Also, exothermic is going to feel hot to the touch because it's exuding heat. Now, endothermic means that heat is absorbing heat. However, that doesn't mean it's going to feel hot. It's going to feel cold. Endothermic feels cold. Now then, now that we've gotten that out the way, we can continue. I can define enthalpy. Oh, brother. All right. So, whatever she has, it's like kind of conflicting with research, but from what I can tell, enthalpy is the amount, like, it's like the total heat in a system, right? The measure of the total heat in the system, I hope. I can identify the enthalpy changes for the endothermic and exothermic process. Well, obviously for endothermic, you're going to be getting more enthalpy because you're getting more energy. And for exothermic, you're going to be exiting enthalpy because there's less energy in the system specifically. So we can go ahead and check that off. I can identify endothermic and exothermic processes from an energy profile. From a graph. You can stop me off. What? Okay, here we got graphs. So remember, endothermic means that it's going to be losing heat. Now, you always have to remember that they're going to be drawn like this with a hump. There's always going to be some kind of hump. And the hump is basically just because a system always has to have some kind of starting energy. So you always have to have a starting energy to get the reaction going. So this would actually describe a exothermic, because this is saying, oh, we are losing energy. This is describing an endothermic because it's saying, oh, we're gaining energy. Our final energy is 750. Our initial was 350. This one's saying our initial was 350, but our final was 250. If the I'm not gonna say that, but maybe it'll help. If the final is more than the initial, then it's exothermic. If it's less, then it's endothermic. Yes. Okay. That's just simples. All right. So we went ahead and did that. I can identify reactants, products, activation energy, and enthalpy on a blah 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 blah. Cool. So, activation energy, what I literally just talked about, it's that. That's the activation energy. The reactants and the products. Reactants react. Am I not in focus? Dang phone. You know, somebody banned me from cursing, so I can't curse. Reactants, the things that are going to react together. They are reacting together. A plus B are the reactants. I don't know why that's a 6. It should say B. There. Reactants, A plus B. The products, they are the product. I'm giving you this. This is the product. Is going to be the final thing. Okay, I think that's all from... I don't think I was cut off from there for too long. Enthalpy. The enthalpy, right? Here, we lost enthalpy. We gained enthalpy. There. How about that? And I hope somebody watches it all the way through. If you did, I'll leave something down below. Like, I don't know, heart emoji. How about that? Right? Alright. Now then, I can identify endothermic and exothermic process from a thermochemical equation. Okay, that's a little bit more... It sounds complicated, but honestly, it's not that hard. And I'm going to flip to a page where it all makes sense. I think it's talking about this. Alright, so we're just going to ignore this writing right here for a second. Please focus. Alright, this is saying we're going to ignore a whole bunch of stuff. Or no, I'm just going to tell you it. Ready? So this is saying 2 boron as a solid. Please tell me I'm in focus. 2 boron as a solid plus 2 hydrogens as a gas plus 36 kilojoules of energy is boron 2, hydrogen 6 as a gas. Now, ignoring a whole bunch of this, the number, it's right there. It's speaking to you. Sorry. Literally, 36 kilojoules of energy. We've gained heat into the system. We're adding heat into this to get this. We've added heat to get to this. We have added this much heat to these two to get this. So it's endothermic. We're basically putting in heat. Now, it's going to look like this, Split it. Split it.